Hi everyone. In this video, I'd like to really start getting into measuring angles using radians. So you can measure angles using degrees or radians, and we're going to spend the first big chunk of the quarter, like 2/3 of the quarter, just focusing on radian measure. Degree measure tends to be a lot easier for people that are already familiar with it. So instead of having you switch back and forth a ton, I'm just going to go ahead and stick with radians for a while until we get really comfortable. Okay, so radian measure. This seems like a weird one, but it actually works out really nicely. We want to picture taking a circle. So here, I'm going to draw this right here. And here, we'll even put it in the XY plane. And if we take the radius of the circle, so this is our R, and we lay it around the outside of the circle. So we take this length, this visualizing radians, there's a link for this in WAMAP. I'm not quite cool enough yet to switch back and forth between webcam and screenshotting, whatever you would call that, screen capture. But it is in WAMAP, so if you want to see a little more high-tech version of this, check it out. It's really nice. Okay, so we take this length, R, and we say, okay, we're going to wrap that around the outside of the circle. So this as well is an R. And we're going to capture that little segment of the circle with an initial side down here and a terminal side up here. So this is still radius R. And the angle that captures, it's called subtends. So the two rays capture this angle right here. I'm going to call it theta. That is 1 radian. So the angle trapped by wrapping a single R around the outside of your circle is 1 radian. If we wanted to go 2 radians, okay, let me see if I can stick with my colors. We would take our radius again, and we would, okay, so here's R. We would wrap it around, so this is kind of approximate, but 1 radian should put us about here. And then we would take another R and tack it onto that, which puts us somewhere out here in quadrant 2. So that's another R, and that's what 2 radians. So this angle right here is 2 radians. Okay, so I actually have this note at the bottom, but I think this is a great time to say it. One of the things that's really wonderful and powerful about radians is that they're unitless. So basically what I'm saying is 1 radian is related to the number of times you've stretched the radius around the outside of the circle. So if I say I've captured the radius 2 times, there aren't units attached. That's not talking about the length. I guess it is talking about the length a little, but it's all about how many times you've wrapped R around the outside of the circle, and the number of times you do something is unitless. It's just a number of times. So radians don't have any units attached to them, and that makes them very nice to work with. In calculus, I think we pretty much exclusively favor radians so that we don't have to worry about weird unit stuff going on. Okay, so we know roughly what 1 radian looks like. We know roughly what 2 radians look like. I actually think I'm a little far into quadrant 2. So how about this for a question? If I want to make it all the way around the circle, how many radians are in the entire circumference of the circle? So 1 full revolution. Right, so from here back to here. Okay, so that actually doesn't seem obvious to a lot of people, but if you think really carefully about what that's really asking you how many times does the radius fit around the outside, the circumference of the circle. And there's actually a beautiful little formula that tells me exactly what the answer is. Circumference equals 2 pi r. means the circumference is 2 pi times the radius. In other words, the radius of a circle will fit around the outside of the circle exactly 2 pi times. So this is all the way around is, let's put an arrow there, 2 pi radians. So I was writing the radians up above, but I've explained the unitless thing. So we don't really need to write radians next to that. If you want to ever jot that down just to keep track, that's okay, but radians are unitless, so not necessary. So this is going to be a really big starting point for us, knowing that 2 pi is an entire revolution is kind of like knowing that 360 is all the way around 360 degrees. And we can start to break that up a little bit more. So for example, if we only go halfway around the circle, and there's our angle, and that's going to be pi radians. So halfway around the circle is going to be half of 2 pi, which is pi radians. And we can do this more. Let me see what I've got next. So let's do some specific examples, and then I'll break up the circle a little bit more for you and show you. Okay, so again, 1 radian is the angle that captures 1 radius laid around the outside of a circle. So what I want to do here is figure out which direction these things are pointing. So let's say this is a rotation of negative pi over 3 radians. I want to figure out where that's pointing. And then I want to see if we can spot some angles that are coterminal. So it's great if you want to pause and try and guess ahead of me and get those coterminal angles. It's really good practice. Okay, so if I want to go negative pi over 3, I was totally getting ahead of myself with drawing. I guess I wasn't really getting ahead of myself because of the definition. Okay, never mind. Sidetracking. Negative pi over 3. So we've said that all the way around is 2 pi, and halfway around this way is pi. So we want to figure out how far around a pi over 3 is. And we want to make sure we're going down instead of up. So if I go all the way across here, this is a negative pi, which means I want to split that up into thirds. So here and here. So if this is roughly negative pi over 3, and then to here would be a negative 2 pi over 3, and then to here would be a negative 3 pi over 3, which is pi. So it's really just recognizing the fractions, right? This is a third of a pi. So if pi is halfway around, then this is basically a sixth of the way around the circle. So this is my negative pi over 3, points me out into quadrant 4. It's going to be a little closer to the y-axis than it is to the x-axis. We're also supposed to spot some angles that are coterminal. So again, I think it's wonderful if you can pause and try and guess them ahead of me. One option that I can see is I could just go the opposite direction and find a positive angle that lands there. So again, we want to count out how many pi over 3s. So we've gone through 1, 2, 3 pi over 3s. This isn't perfect, but it's close. And then 4, 5 pi over 3s. Okay, so I should be really clear that this is one of them. The y-axis is not a pi over 3, so we actually skip right over when we're counting pi over 3s. We go 1, 2, 3, 4, 5 pi over 3s is one angle that has the same initial side and terminal side. Another really good way to think about this is all the way around is 2 pi. But we want to count in pi over 3s, so recognizing that that's 6 pi over 3s can be really helpful. If you go 6 pi over 3s, you've gone all the way around, which means if we want to take away a single pi over 3, we'll be left with 5 pi over 3s. That's a great way to think about it. Another way we could do this, I'm going to run out of room fairly quickly. We could continue in the negative direction, but go all the way around until we get back here. In that case, I've gone negative 6 pi over 3s all the way around. and then one more pi over 3, which means negative 7 pi over 3. So again, anytime you're heading the clockwise direction, it's going to be negative. So negative 6, and then one more is negative 7. We could, I don't have any more colors, but we could go all the way around the positive direction and then an additional 5 pi over 3 to land here. So that would be 6 pi over 3 to get all the way around, and then 7, 8, 9, 10, 11 pi over 3 to land back here. Let's pick another one. 11 pi over 3 is a great one. Basically, anytime you add or subtract 2 pi, so 6 pi over 3 is in this case, you're going to get another coterminal angle. A full lap around the circle puts your terminal side right back where it started. So 11 pi over 3 is great. So is 17 pi over 3 or 23 pi over 3, so on forever. There's infinitely many angles that work. Negative 7 pi over 3 is great. So is negative 13 pi over 3 or negative 19 pi over 3. There's lots of them. Okay, let's look at 3 pi over 4. I don't know why I'm drawing circles. I'm not really ready for that yet. Here, we'll move over. Okay, so now we want to look at counting by pi over 4s. So a pi over 4, let's see. So if we want to take pi, which is halfway around, and divide it into fourths, half of pi would be 1 quadrant. Half of pi is basically a 90-degree angle. A quarter of pi is going to split a quadrant right down the middle. So here are our pi over 4s, and this continues around. Maybe we'll go ahead and do this now and skip the next slide. So we should be able to count around in multiples of pi over 3 or pi over 4, or even a little bit smaller than the pi over 3, pi over 6s. Those are the ones that we want to be good with. So this is what counting out pi over 4s would look like. You'd go halfway through a quadrant. So there's 1 pi over 4, 2 pi over 4s, which is the same as a pi over 2, so lots of reducing fractions. 3 pi over 4s, this is the one we're looking for, so I'm going to go ahead and draw that in. 4 pi over 4s is a pi. 5 pi over 4. 6 pi over 4 is, can I do it in my head? 3 pi over 2. If I just think about what it is, I can do it. 7 pi over 4, and all the way around is an 8 pi over 4. Again, it's nice to think about what those all the way arounds are for these sort of problems. Okay, so 3 pi over 4 is this one. If we want to find something coterminal, we can start off the same way. We can first just say, well, what if we just go the opposite direction? So now it's going to take a negative angle, and it's going to be negative 1, 2, 3, 4, 5 pi over 4s. So a negative 5 pi over 4 works. Again, you have two choices. You can just count like I did, negative 5 pi over 4, or you can say if all the way around is 8 pi over 4, and I've already gone 3 pi over 4, that leaves me 5 pi over 4. Excuse me. We could also go positive direction all the way around once, and then continue until we get back to that same terminal side. So that one's going to be 8 pi over 4s plus another 1, 2, 3, so 11 pi over 4s. And then again, anytime we add or subtract 8 pi over 4, we're going to get another one. So we could subtract 8 pi over 4 from this one. We'd get negative 13 pi over 4s. We could add 8 pi over 4 to this one. We'd get 19 pi over 4s, and so on and so on and so on. So you should be able to get as many as you want, but do try and practice getting at least one negative and one positive to make sure you're getting good at spotting these things. 17 pi over 4. Oh man. Okay, so let's see if, so we're counting pi over 4s again. Okay, so there they are, and that includes the axes. The axes are pi over 4s as well. If we want 17 of them, we just said that 8 pi over 4 is all the way around, so we've gone 8 pi over 4, And then 16 would be another 8 pi over 4. And 17 would put us right here. So this is, there's some round and round and round happening, but this is our direction, right smack in the middle of quadrant 1. So 2 full laps around, and then we have 1 pi over 4 left to put us out into quadrant 1. Okay, so in this one, the one that jumps out at me right away is that this is coterminal with just a plain old pi over 4. We don't need to go round and round and round and round to get there. We could just start on the positive x-axis and head up a single pi over 4. Which means it's also going to work if we go the other direction, -7 pi over 4. So again, you can either count them out, 1, 2, 3, 4, 5, 6, 7, or you can say all the way around is 8 pi over 4s. I've already used up one of them, so I would have to go back 7 to get to that same location. What if we only went one time around? So the original one was twice around. So what if we only go once around and then a pi over 4? So that's 8 pi over 4 and then 9 pi over 4. And you could do more negative by subtracting 8 pi over 4. So -15 pi over 4 would work. You could add another 8 pi over 4 to this and get 17 pi over 4. So any of those are good. Infinitely many possibilities. Just see if you can snag a few. Okay, one more here. If we go -10 pi over 3s. Oh, I keep trying to draw my circle. We'll be doing lots of circles, so you will understand why I'm so stuck on that in a little bit, but we don't really need it right now. It's okay if you want to draw it, but I think it just makes more mess in my pictures. Okay, so pi over 3s. There are 6 pi over 3s, excuse me, an entire rotation. So we're going backwards. If we go once around, that's 6 pi over 3s, and then we need to go 4 more. So remember, a pi over 3 splits up half the circle into thirds. So basically it splits the whole circle up into sixths. Okay, so those are my 1, 2, 3, 4, 5, 6. So if we've gone all the way around, that's -6. Here's -7, 8, 9, 10. So this is my direction. Once again, I think the easy one that stands out is instead of doing all that round and round backwards, we could just either start on the positive x-axis and go positive angle, which is 1, 2 pi over 3s, or we could start positive x-axis and go the other direction until we get there, which is -1, 2, 3, 4 pi over 3s. I guess I should have known that from the counting we did earlier. Oh, -4 pi over 3s. We already did the next one, which is -10 pi over 3, but you could go another 6, -16 pi over 3 would work. Or here you could go 2 pi over 3 and then another 2 pi, which would be 8 pi over 3. So again, with that one, we'd say we've gone all the way around, which is 6 pi over 3s and then an additional 2. Okay, so you have some practice with this. You basically want to be really good at visualizing how to break the circle up into pi over 4s, which is 8ths of the whole circle, or pi over 6s, which would be 12ths of the whole circle, or pi over 3s, which are actually multiples of pi over 6 as well, but it's kind of nice to think of them on their own, so splitting the circle into 6. So let's see, I already broke up pi over 4s fairly nicely, but let's just look at the pi over 6s really quick. So we'll do a ton of this with unit circle. Here, let me use this color. Oh, again, you don't really need a circle. This is just me not being able to not think about the unit circle since it's coming. Okay, so if we think of a full revolution as 2 pi, so we start at 0, 2 pi is coterminal with 0, as is 4 pi or -2 pi. Over here is pi. We want to split, so I'm just going to look at pi over 6s. We want to split half of the circle into 6s. So pi is half of the circle. If we want 1/6 of that, we've already looked at thirds. Thirds breaks us up roughly like this. We want to go even further. So let's say right here, and then right here, and then right here. So I look a little bit crooked. That doesn't look like perfect 6. But if you can imagine splitting the first quadrant into thirds and splitting the second quadrant into thirds, the second quadrant doesn't actually look so bad, but let's move that a little bit. Okay, so we start at 0. This is 1/6 of pi, right? 1/6 of the top half of the circle. So that's a pi over 6. This is 2/6 of pi. 2/6 of pi reduces to a pi over 3. So this is what I was saying earlier. The pi over 3s are multiples of pi over 6, but we can think of those sort of separately just to simplify our life a little. When we're working with pi over 3s, we don't really have to visualize all the pi over 6s. Here at the top, we get to 3 pi over 6, which reduces to a pi over 2. Next one, we're at 4 pi over 6, which is 2 pi over 3. So we've already looked at that one. And then we get a 5 pi over 6. And then we get pi. So there's the top half of the circle. We should be able to continue. Okay, so that looks decent. Split the bottom into 6 as well. So this would be, so this was 6 pi over 6, which gives us pi. 7 pi over 6 is the next one. 8 pi over 6 after that, which reduces to 4 pi over 3s. 9 pi over 6 is straight down, which reduces to 3 pi over 2s. 10 pi over 6, which reduces to 5 pi over 3s, and then an 11 pi over 6. And if we want to do the last one, it would be a 12 pi over 6, which is our 2 pi that we've already marked off. So this is what the circle looks like broken up into pi over 6s. On the last page, we looked at breaking it up into pi over 3s or pi over 4s. We should definitely also be able to break it up in pi over 2s or pi's. Those should be really easy. So if you want to count pi over 2s, it's just one quadrant. So we'd go 1 pi over 2, 2 pi over 2s, 3 pi over 2s, 4 pi over 2s, and so on. And of course, you can go the opposite direction. So for this one, if we went the opposite direction, it would just flip-flop these. Negative pi over 6, negative pi over 3, negative pi over 2, and so on. Okay, so you want to be really good at visualizing those nice multiples. We're going to work with those a ton, and we're actually going to memorize some other information about points at the end of multiples of pi over 4 or pi over 6. All right, thanks for watching.